Welcome to thermal fluid science. We're studying a heat conduction problem. We want to find the temperature distribution inside this solid. It's a very long cylinder. It's hollow inside. So in this space inside there is a flow at a certain temperature T infinity that's supposed to be constant. So we also have heat transfer convection coefficient of this flow H. The inner radius of the cylinder is R1 and the outer radius is R2, and the outer surface of the cylinder is constant and uniform. That's Ts. We also have the hypothesis that T infinity is larger than Ts, so heat flows from the inner part of the cylinder to the outside. Since the cylinder is very long and the condition is uniform along the angle, we can consider the flow to be one-dimensional, and also we have a steady problem. So I said we want to find the T as a function of the radius R. So to do that, we study the heat conduction equation. So for a cylinder, we can use the equations in cylindrical coordinates. So we can write it K, where K is the thermal conductivity of the material of the cylinder, and that's supposed to be constant and uniform, divided by R, d dr, R dt dr. We note immediately that we can use the d as a simple derivative, not the partial derivative, because the conduction problem is one-dimensional. So then in general we could have some heat generation, but this problem, the heat generation is 0, so this goes to 0. And as we said, we don't have the unsteady term, so the rho Cp partial T partial time is also 0. So this equation then it simplifies to dr of R dt dr equals 0. So K does not enter the problem because we can simplify. We also simplify R because that's always larger than 0. So we reduce the problem to an ODE, and we can integrate this ODE. This is second order ODE, so we need two boundary conditions. So boundary condition. The first boundary condition is the conduction boundary condition in the inner part of the cylinder. So here at R1, so the convected heat from the hot fluid is transferred through conduction through the inner part of the cylinder. So essentially, as we've seen it before, it's energy balance at the surface. So we have H T infinity minus T at R equal R1 equal minus K dt dr at R equal R1. The second boundary condition is at the outer surface of the cylinder, so we have T at R equal R2 equal constant temperature Ts. So we can integrate the equation now. So let's rewrite it for clarity. We have First step in the integration, we obtain r dt dr equal a constant c1, that's a known. So dt dr equal c1 divided by r. We integrate again, we get t of r equal c1 log on base e of r plus c2. And that's the expression for the temperature profile. So we need to find C1 and C2, and we use the boundary conditions. And note that when we have cylindrical coordinates in conduction problem, it's not surprising to find a log that describes the temperature profile. So we use the boundary conditions to find C1, C2. So if we use the first boundary condition, we have h t infinity minus c1 h log r1 minus h c2 equal minus k c1 divided by r1. Now, second boundary condition, simpler, c2 equal ts minus c1 log of r2. We have two unknowns, c1 and c2. We have two boundary conditions, so we can do a bit of algebra, and that's left for exercise. So you can pause the video and do yourself. We have solution c1 equal h r1 that's the first constant, and we note immediately that's smaller than 0. And we see why this is important to interpret the physics. And C2 is Ts minus log R2 times H R1 K plus so we have C1 and C2, and we find T of TR. So we substitute C1 and C2 in the expression we found before, and we obtain the solution as T of R equal Ts plus H Very good. So as an exercise, you can check the boundary conditions. So you set, for example, R equal R2. Here we get the log of 1, that's 0. So all this term is 0. And then we get the temperature at R2 equal to S. So that's a good check for the second boundary condition. And we can do the same for the first boundary condition, the convection-conduction boundary condition. So we can also sketch the temperature profile. As a function of R. So this is R1, R2. t, and indicate the prime, use the prime to indicate the second derivative with respect of r, is equal to minus c1 r2. And r is always positive and c1 is negative, as we said before, so the second derivative is always positive. The second derivative indicates the curvature of the temperature profile. So we know that we need to sketch a temperature profile with the positive curvature. So that will look something like this. So that's a positive curvature. And always, temperature is always decreasing from the inside to the outside, because T prime of R is equal to C1 divided by R. And C1 is negative, R is positive, so we have a decreasing temperature profile. And that's also expected because we are heating the inner part of the cylinder, and so heat flows outside. So Q flows outside. One thing we note is that the slope of the temperature profile is higher at R1 and lower at R2 because the heat flux Q dot at R equal R1, that's equal to minus K dt dr at R equal R1, is larger than Q dot at R equal R2. How can this be? Well, because for conservation of energy, we must have that the BQ, and BQ is the heat rate in watts at R equal R1, must be equal to BQ dot at R equal R2. So this is in watts. But if we expand this expression, we have minus K A1 dt dr at R equal R1 equal minus K A2 dt dr at R equal R2. Since A1 is smaller than R2, because R1 is smaller than A2, then dt dr at R equal 1 must be larger than dt dr at R equal R2. So this is a good check. And remember, when you do this kind of conduction problem, it's always good to check, of course, the boundary conditions and whether the solution satisfies the equation, but it's always a good practice to carry out global energy balance like we've done now. That's it for today. Thank you very much, and I'll see you in the next video. Bye.